Okay, here we are again. This looks familiar for what we had talked about last time. So there's our one-sided limit definitions. And just for fun, let's put this one up here for a limit. Limit means you're coming from both sides. So we've got these guys here, so we can rattle this off really quickly. For every epsilon greater than 0, there exists a delta greater than 0, such that, okay, if what? How do we take care of both of those pieces all at once? Yep, you guys just are screaming it out there. 0 less than the absolute value of x minus a, less than delta than the absolute value of f of x minus L is less than epsilon, right? Okay. Okay. In all of these problems, right, we are saying that the limit is equal to L. For every single one of these problems, right, L is a real number. A single, so that's why there can't be two, right? Like negative 1 or 1 and negative 1 and 2, right? Okay, just doesn't work, okay? A single finite, as in not infinite, right? Real number. Okay? So we saw a way that a limit doesn't exist if the left-hand limit and the right-hand limit are not going to the same number, right? Because we've seen a couple of examples like that, right? And how that violates the definition of limit that we have to be able to be on either side of A. And then where does L live? Okay, good. Where does L live? L lives on the y-axis. It is just a number that lives here that is and what is epsilon doing? Measuring how far away from that limit the y value of the function can be at any one time for a given delta, right? Okay? So there's our epsilon, right? That's L plus epsilon, and that's L minus epsilon, yes? Okay, so this is critically important. We've already seen one way where a limit doesn't exist when our left and right hand limits don't go to the same number, right? Okay? So the idea of what the book calls infinite limits, which I don't like to call that, is the idea, it's really when does another way the limit does not exist, okay? And so that's really what the book means when it talks about infinite limits. It's limits that do not exist in a very specific way. They either don't exist by the closer x gets to some number, that the y values of the function grow unbounded positive, right? Shoot to the sky and never come back, right? And keep on going forever and ever. Or they grow unbounded negative, okay? So unbounded growth. And so we want to see how to adjust these definitions we now know and love for this case of a limit not existing because of unbounded growth. And there's other reasons why limits don't exist. Some of your problems in the section 2.2 and in the reading in 2.2 also have you exploring places where a limit doesn't exist because not because of unbounded growth as x gets close to some number, but because the function just oscillates back and forth like crazy and just never settles in on any one number. The function stays bounded, but never settles in to be able to have an epsilon band of any small size around a final limit, right? Okay, and that's a different kind of reason for a limit not to exist. We will often just call that like a wild oscillation or something, or because of oscillation not existing. Okay, so what does it mean if we say a limit doesn't exist because it grows unbounded and positive? Okay, this is what your book would call an infinite limit. So we'll talk about this. Now we're going to see how would we adjust this. Definition. Now, your book says a limit equals infinity. We already said we don't use that kind of bad notation. We can never equal infinity. Infinity is a concept. You can't equal a concept. So the limit goes to infinity, right? We'll put an arrow there. Goes to infinity is kind of maybe what you like to say because it's what's sitting here in front of you. But really what we're saying is the limit as x approaches a of f of x grows without bound positive. That's really what this says, right? Grows without bound positive, right? So that's really grows without bound, right? And grows positive, right? Because numbers go both directions without bound, right? Positive or negative. So it grows positive without bound as x gets close to a. Yeah? Okay. So that's what we want to, another way, a limit does not exist. So when you say this, we're saying the limit doesn't exist. Not only are we saying the limit doesn't exist, but we're also saying, hey, and here's some more information about why that limit doesn't exist. When x gets close to a, the y values of that function for x near a start growing bigger and bigger and bigger, and the closer I'm going to get to a, they're going to grow without bound positive. Yes? Okay? That's the idea. This limit does not exist. Okay? Which is different from left hand and right hand limit equaling some finite number and them not being the same, and the limit not existing for that reason. Okay, so how do we adjust this definition, right? That's the big goal. What is different, okay? Well, this hasn't changed, right? X is still approaching a, so we still want to be able to talk about the distance between, right? The distance between x and a being smaller than delta, right? X only ranging at most delta units away from a, and x not being equal to a because it's a limit, and we know that that means, right? X doesn't equal a, right? Yeah, that's what it means. X doesn't equal a. And so, you know, what do we have here? We got a plus delta, right? We got a minus delta, and x still lives just in there, yeah? Here's our delta, right? So we're golden there, we're good to go. And what changed? Well, we have kind of an infinity where there was an L, right? So, you know, would it make any sense to be like, oh, well, let's just change the L to an infinity, right? And we'll make this the absolute value. Don't even write this down. The absolute value, because you know what's coming, right? Does that make any sense? What does this mean? The distance between the y value of the function and infinity is smaller than some number epsilon. Does that make any sense? Like, can you measure that? How close am I to infinity? Well, infinity is a concept, it's not a number, so it's hard to measure closeness, right? So that makes no sense, right? No sense whatsoever. So you can't just plop an infinity in where there's an L. Yeah? You just can't do that. It makes no sense. You can't say the distance between the y value of the function and infinity. That makes no sense. So we have to get rid of this. And we have to come up with a new ending. It's a new ending for this idea. And since it's a new ending, and, you know, epsilon, this number, you know, it's just a positive number, but when we think about epsilon, you know, we often think of something small, right? I want this one more time to make sure that this is recording. Out of COVID practice of making, okay, yes, it's definitely recording. All right, when we think about epsilon, right, we think about something small. You agree? Good, okay. And so, I'm going to use epsilon in this definition because that makes us think about, you know, how close are we to something? And you can't be close to infinity. What are we trying to say? we're trying to say the y values grow without bound, right? They're big, yeah? They get big. And so, we'll often use a big letter, okay? And the letter we often use is the letter M, a capital letter M. A capital letter M. It's still some positive number. So now we're saying for every positive number M, there's always got to be some distance away from A. That if you control the input, I can tell you something about the output. As long as I'm close enough to A, I can guarantee what? Well, it's not this anymore, right? Because we're not talking about getting close. Yeah? Well, what would we want to say? If I'm going to try to say this thing grows without bound, and I'm thinking of M here as being some kind of big positive number, 10 billion, 40 quadrillion, right? Okay. 10 to the 93. Yeah, okay, a big positive number. This is for any positive number, but now we're talking like, we think of this, that's one of the reasons why I write capital M. A big positive number, if I'm saying these functions grow without bound, this function grows without bound as x gets close to A, then what am I saying? Well, you give me any big positive number, I can get close enough to A so that, well, what would be the inequality relating this and this? If this guy is going to grow without bound, and this is some big fixed positive number, no matter how big it is, but it's fixed, right? Then you, in order to claim that this thing grows without bound, you want to claim, I think I hear it, yeah? That these, I can always get close enough to A so that these guys are bigger than any big number you want to give me. Yeah, does that make sense? Yeah? So if you know, we've got, you know, right? And if our M is way up there, right? Then maybe we can find a delta where, okay, if we, as long as we stay in here, right? As long as we stay in here, in this region, for x, then what's going to be true about all of our f of x's? All of our f of x's are going to live up there, right? They're going to get bigger, right? They're going to be bigger. And then suppose we make M bigger, right? We go through the ceiling and go up to the third floor with M, right? Well, then we can just change delta. It's the same, we guarantee we can change delta so we can get close enough so we can make sure that all the y values of the function for those x's are bigger than that M. And maybe we go to outer space and beyond, and that's what this is saying, right? We can always get close enough to A so that we can make the y values bigger than any real number you can give me, even if that real number is the distance to, you know, some galaxy far, far away, okay? So that's what we mean when we talk about a limit that doesn't exist because it grows without bound, or what your book says, equals infinity. Silly thing to say. All right. So let's see how we would then switch up these guys now that we're good with this. Let's switch up these, okay? How's this one going to change? If it's a right-handed limit and we're only talking about if the function only grows without bound if you approach A from the right, well, what's going to be the only difference? It's all the same thing. This guy's going to be your M. That's also the same because that's saying, oops, didn't mean to erase that piece. That's really making x be to the right of A and close. And then how is this going to change? We're not going to be measuring distance, right? We're just going to say same thing. F of x is bigger than M, yeah? And left-hand limit, you guys got this now? Good. Epsilon becomes an M, yeah? And this piece becomes the y values of the function are bigger than any number out there in the world you can give me. I can always get close enough to A, this kind from the left, yeah? Okay? One-sided limits not existing, yeah? Oh, and we're not saying equals infinity. We're saying grows without bound. This grows without bound. Those are our definitions. Does that make sense? It's right there, yeah? Okay? Let's look at an example, okay? So let's look at, let's see, what might I look at for you? Okay, let's look at, section 2.4, and this is problem 9. So this is 2.4. This is number 9 in your homework, in your web assign, right? This really 2.4 number 41. Okay, so actually maybe I should write that. 2.4 number 41. Okay, 2.4 number 41. That's number 9 in your web assign, and it says this. How close to -6 do we need, or do we need to take, x so that 1 over 1 plus 6, or yeah, 1 plus 6 to the 6, sorry, 1 over x plus 6, I knew that didn't look right. 1 over x plus 6 to the 6 is greater than 1,000,000. Okay? So that we're guaranteed that's satisfied. And we want the largest possible value. Okay? Okay? How close to -6 do we need to take x such that, so what are we really being asked here, right? Hopefully you're seeing it, okay? How close to -6, right, is x? Well, how do we measure that? If I'm gonna say how close to -6 is x, right? That's the same as saying the distance between, right, x and -6, right? The distance between x and -6. We want that to be, we want those to be close. So less than, hey, some number maybe delta, right? Delta is the distance between x and -6. So what is this really asking you? Yeah. What is delta? Yeah? So if we identify our players here in this problem associated with this definition, what is A? I hear you. A is careful, right? A is -6. Now, it's true that this is the absolute value of x plus 6, right? X minus a -6 is x plus 6. But that's not as useful a way to write it, right? It's not as useful a way to write it to recognize that, hey, wait, A is -6 because the absolute value of the difference of these two things, right? The distance between them. Yeah? Okay? All right. So A is -6, right? We're being asked for delta. What else were we just told? Yeah, like, does this not look just like that? Right? So what is f of x here? F of x is 1 over x plus 6 to the 6. Yep. And what is m? M is 1,000,000. Right? So this problem, right, is really asking, okay, what should delta be? What's my input control if my output needs to be bigger than 1,000,000 always? Does that make sense? That's a good finance. If you're a financial planner? That's a good question, right? Okay, all right, so, what do we do, right? So, this problem is really suggesting that, that's easier to do with a whiteboard and a marker, right? What is this problem suggesting? Is the limit as x goes to, what did we say a is? Right, -6. The limit as x goes to -6. What's f of x? Oh yeah, 1 over x plus 6 to the 6th, right? What might we be able to say about that limit? Here you're just doing it, this problem is simply asking you for one value of delta. But the idea is that, hey, maybe there's a value of delta for every m, not just for m a million. And if there is a value of delta for every m, not just for m a million, then you'd be able to make the claim that this limit, right, does what? Grows positive and unbounded. Goes to infinity. An infinite limit does not exist, right? Okay? More information about how it doesn't exist. You know it grows positive and unbounded. Yeah? Okay? Okay? And therefore, we would have a vertical asymptote at x equals -6, if that were the case in this problem. And the function would blow up. This is saying, right, it blows up positive, the y values get positive regardless of whether we're on the right of 6 or on the left of 6, right? Because we don't have a little plus or minus up there, right? So that tells you that if this guy's blowing up, then the function kind of looks like that near -6, right? It's way up, it's doing that, yeah? Does that make sense? Okay? Okay? Now we can draw our m, and we have our delta to be so as close as we want, and the y values will grow unbounded positive regardless of which side we're on. Okay, so for this problem, well, what would we then be doing, right? Well, we're essentially solving this inequality so that we can come up with what delta is, right? We're solving this inequality. Now looking at this as x plus 6 is kind of more useful if we're trying to actually come up with delta, right? Because I know this inequality holds. My question is, what inequality holds on the absolute value of x plus 6, right? That's the question. So if we were going to do that, right, let's just go through a few steps. So I could, x plus 6 to the 6th power is positive because 6 is even, right? So I can multiply both sides of this inequality by that, and that won't change the sign of the inequality, yeah? And a million, right, is also positive, so I can divide both sides of this inequality by that, and that won't change the sign, right? Okay? And of this inequality. And so if I do that, that gets me my x plus 6 to the 6th, at least up in the numerator instead of the denominator, right? So 1 over 1 million, right? We can talk about what that is here in just a little bit. Or you can think about your rules of exponents and how you can write that as power of 10, right? And here as power of 10, a negative power of 10. Those are all good things for you to review for yourself. X plus 6, right, to the 6th, right? Multiply both sides by x plus 6 to the 6th, and divide both sides by 1,000, yeah? Okay? Okay, and then, right, now, a lot of you might say, oh, just take the 6th root, right, to get x plus 6, but again, it's the same idea of our square, you know, if we had a square here and we took the square root, we get the absolute value of this guy, not just plain old x plus 6, right? Because this could be negative, and when it's squared, or when it's taken to the 6th power, it gets positive, yes? Okay? And so if I take the 6th root of both sides, I will get the absolute value of x plus 6 has to be less than this guy, 6th root. Yeah? Right? To the what? Not right. There we go. 6th root. Yes? Okay? And what was I looking for? Oh, lo and behold, right? What was I looking for? I was looking for delta, which is a bound on the distance between x and negative 6, which is also a bound on the absolute value of x plus 6, right? And this less than delta, this less than delta, right? Okay, so it doesn't matter. It matters which direction the arrow is pointing in a less than sign, right? Yeah, okay, as far as which goes which. So that's relating this piece, finding the delta, to what you need in order to guarantee the end result. Okay, so here for these problems, in general, delta will be a function of m, where in our problems that we've been doing, delta is a function of epsilon, right? So clearly this delta depended on the number a million, which was the m for this problem. Yeah? Okay, I'll let you guys finish the rest of that problem. And let's see what else. Let's do a couple related to one-sided limits now. Okay? So this was related to section 2.4. Now, let's go talk about the same idea with one-sided limits. Which is why I didn't erase all the rest of that. Just I knew I'd come back to it. Maybe you were wondering why I was squeezing everything in right there. That's why. Okay, we ready to keep going? Alrighty, so let's see what we got here. Let's just take a look at another problem. And by the way, again, as I said before, when the WebAssign problems say a graphing calculator may be useful, we don't use calculators, right? So in general, you either have a way to think about that problem, or you go look in the book and that problem is precisely in the book and they've already produced a graph for you, okay? So there's a little hint. All right, let's take a look back at a couple of 2.2 problems. So this one is number 9 in the 2.2 WebAssign, but it's 2.2, number 31, okay? So let's look at this. We've been given the limit as x goes to 9 from the right of x plus 1, this marker I don't like, it's not that good, divided by x minus 9. Can you see that? I'm gonna move this one over here so I don't keep using it. I'm gonna check and see if I can see that on the video. You can use this, I can see that. You can use this time to think about what you think that limit is. Okay? All right. So let's think about this, okay? The limit is x is going to 9 from the right. So what do we know, right? What does this mean? It's a limit, right? So it means x isn't equal to 9, yeah? Okay? X is not equal to 9. But what? It's a right-hand limit, so what do I even know more? Where is x? Related to 9. Yeah, to the right of 9. Yeah? X is to the right of 9. So if x is to the right of 9, x is bigger than 9, right? X is bigger than 9 is something that tells me. X is at 9 and x is bigger than 9, yeah? So we already guessed that there's some kind of problem going on here, right? Because if we're talking about what's happening as we get like infinitesimally close to 9, right? That's what this is saying. We're right here. We want to get, you know, within delta units, right, of 9, okay? You know, it's screaming out at you here, if we did plug 9 into this function, right? If we plugged 9 into this function here, right? Then what would we have? We'd have 9 plus 1, right, which is 10, right? Over 9 minus 9, which is 0, yeah? And have we already talked about this kind of, you know, if we have a number that's not 0 over 0, what do we know? Yeah, it doesn't exist, right? Okay? Now the limit means x is getting close to 9, right? Not equal 9, okay? And so our question is, well, what's happening here? And the question is as x gets close to 9 from the right, does this function grow without bound? Positive, okay? Well, so you have a hint already that this limit might not exist. The numerator, x is close to 9, we're adding 1, right? So any value of x close to 9, I add 1, this numerator is going to be positive, right? Yeah, the numerator is going to be positive. The denominator, tell me about that. Is it positive or negative? I mean, it's not 0 because x is close to, it's a limit, right? X is bigger than 9, right? Okay? So if x is bigger than 9, x minus 9 is positive, right? So it's positive over positive. But the fact that the denominator is getting closer and closer and closer to 0, because this is one of our nice little linear limits, right? If I look at that, and so this is another reason why, man, we want some rules, right? We're tired of these drawings and proofs. In definitions, we want to start utilizing the things that we know so we have rules that will allow us to more easily evaluate these limits, right? That's where we're heading. So this is our nice linear function. This is a graph of x minus 9, right? So there we are, negative 9, right? Here's our line, slope of 1, yeah? And as x gets close to 9 from the right, here's 9, yeah? And if x is getting close to 9 from the right, then what's happening? Okay, I go to the right, and I go to my nice linear function, x minus 9, right? And then I go there, and then I go up, then I get closer because I approach 9 from the right, right? And then I go there, and I keep approaching 9 from the right. And what happens to my y values? The y values are all getting closer and closer and closer to the y value of 0 there, right? On the y-axis, yeah? Okay? And so this limit is 0, yeah? Okay? So what we've got is something that's staying positive, right? Something that's staying positive and is some finite number, 10, right? If we look at just the limit as x goes to 9 from the right of the graph of x plus 1, right? That's going to be 10. And over something that is going to 0, but going to 0 through positive numbers, and that allows us positive over positive. This is going to be unbounded growth, and it's positive over positive, so that stays positive, and therefore we can say this guy is going to infinity. Okay, now we could use the definition to show it, but this gets a little bit harder, okay, in the definition. So we've got this idea. What's happening with this function, okay, from this analysis, from this limit, when x gets close to 9 from the right, I still have a vertical asymptote, right? So this guy is giving me a vertical asymptote. At x equals 9, but what do I know from this? Only that on the right, the function is growing big and positive. Yeah, does that make sense? To the right of 9, to the right, it's gonna get huge. Yeah? I don't know anything about the left of 9 unless I do what limit? Yeah. You guessed it. the left-hand limit, yeah? So what would the left-hand limit for this one say? The limit as x goes to 9 from the left, right, of x plus 1 over x minus 9, yeah? What does this mean? X isn't equal to 9, right? Because it's a limit, right? It's a left-hand limit. A is 9, right? So what do I know? X is less than A. X is smaller than 9, right? Because here's 9, and X is going to approach 9 from the left, right? So X is less than 9, yeah? Okay? But X is close to 9, right? X is close to 9. We're looking for some nice little delta interval, or delta to the left of 9. The idea is being close to 9. So X is smaller than 9, but close to 9, right? So tell me about this expression, right? Well, if X is small, if I have X plus 1 and X is smaller than 9 but close to 9, then that is a positive expression, yeah? Right? And if X is smaller than 9, and I'm thinking about X minus 9 though, X is a number smaller than 9, then X minus 9 is smaller than 0. X minus 9 is negative, right? If this guy's less than 9, I subtract 9, I have something negative. So the denominator here is negative. So now I have positive over negative, and positive over negative is negative, right? Yeah? Good. Positive over negative is negative. So what do we say about this? Same idea, X is getting close to 9. This denominator, right, is getting close to 0, because the same would be true if we did that one, right? And we would just be approaching from here though now, right? X would be to the left of 9. Sorry, I'm trying to not block you. X is to the left of 9, I come here, and I go there, right? Then I get closer to 9, and then my numbers went up. And then I get closer to 9, and my numbers went up. And the closer I get to 9 from the left, my numbers converge on 0, right? So the limit as X goes to 9 from the left of X minus 9 is 0 here from the graphical viewpoint, right? So the denominator is still going to 0. In the same way, we could look at the graph of X plus 1. The numerator is going to 10 still, because X is still getting close to 9, and that's still X plus 1. And we've seen how these linear guys work. So I've got positive over negative. The result here is negative, but we still have unbounded growth. So what do we think we call that? Yeah, right, this limit, I hear you, as X goes to 9 from the left of X plus 1 over X minus 9. Grows unbounded, negative. Grows unbounded, negative. Grows unbounded, negative. Yes? Okay? Goes to negative infinity. Okay? Again, your book would call that another infinite limit. So what does that mean? The graph of this function looks like X plus 1 over X minus 9. If X is a little bit to the left of 9, if I'm within some delta unit, then I can guarantee what? That the Y value is going to be super, like going way down there, right? So the idea now is, okay, I'm going to pick some value here, right? Maybe we'll call it N, and I'm going to say that I want to be able to pick a range of delta, right? 9 minus delta, whereas if X is in that region, then the Y values are always smaller, right? Anything in there is smaller than any really big negative number, yeah? So we just discovered how to write this, yeah? So the limit as X goes to A of f of X goes to minus infinity, grows negative without bound, right? Grows negative without bound. Then we usually use an N. And tell me, was N positive? No, it's on the y-axis, it's on that part down there, right? N is not positive. So for all N negative, right? There exists a delta greater than 0, such that if A minus delta is less than X less than A, fine. We're still in the left-hand limit here, right? Then what would be true? My Y values of my function, my f of x's, for any x in here, would be below N, right? below n. So what's the relationship there? F of x is smaller than that negative number n, right? Yeah, does that make sense? F of x is lower than n, yeah? I can always make f of x more negative than n, no matter what negative number you give me, and how far down it goes, right? And so we very easily just walked through that guy. So hopefully you can, for yourself, write the one for limit as x goes to a from the right, and just the plain old limit as x goes to a, because you know how that changes just this part, right? If they're going to minus infinity, then these parts stay the same. Yeah? Yeah, yeah? We're good here? Awesome, awesome, awesome. Okay, so you are utilizing your knowledge of graphs for some of these. And some of the infinite limit ones. Whoops, I'm getting a phone call. I'm gonna stop this video right now. It's a good time to stop, actually. I'll be back with another video.